Bitcoin mining. Alice's transaction is now propagated on the Bitcoin network. It does not become part of the blockchain until it is verified and included in a block by a process called mining. The Bitcoin system of trust is based on computation. Transactions are bundled into blocks, which require an enormous amount of computation to prove, but only a small amount of computation to verify as proven. The mining process serves two purposes in Bitcoin. 1. Mining nodes validate all transactions by reference to Bitcoin's consensus rules. Therefore, mining provides security for Bitcoin transactions by rejecting invalid or malformed transactions. 2. Mining creates new Bitcoin in each block, almost like a central bank printing new money. The amount of Bitcoin created per block is limited and diminishes with time, following a fixed issuance schedule. Mining achieves a fine balance between cost and reward. Mining uses electricity to solve a mathematical problem. A successful miner will collect a reward in the form of new Bitcoin and transaction fees. However, the reward will only be collected if the miner has correctly validated all the transactions to the satisfaction of the rules of consensus. This delicate balance provides security for Bitcoin without a central authority. A good way to describe mining is like a giant competitive game of Sudoku that resets every time someone finds a solution, and whose difficulty automatically adjusts so that it takes approximately 10 minutes to find a solution. Imagine a giant Sudoku puzzle, several dozen rows and columns in size. If I show you a completed puzzle, you can verify it quite quickly. However, if the puzzle has a few squares filled and the rest are empty, it takes a lot of work to solve. The difficulty of the Sudoku can be adjusted by changing its size, but it can still be verified quite easily even if it is very large. The puzzle used in Bitcoin is based on a cryptographic hash and exhibits similar characteristics. It is asymmetrically hard to solve, but easy to verify, and its difficulty can be adjusted. In the previous chapter, we introduced Jing, an entrepreneur in Shanghai. Jing runs a mining farm, which is a business that runs thousands of specialized mining computers, computing for the reward. Every 10 minutes or so, Jing's mining computers compete against thousands of similar systems in a global race to find a solution to a block of transactions. Finding such a solution, the so-called proof of work, requires quadrillions of hashing operations per second across the entire Bitcoin network. The algorithm for proof of work involves repeatedly hashing the header of the block and a random number with the SHA-256 cryptographic algorithm until a solution matching a predetermined pattern emerges. The first miner to find such a solution wins the round of competition and publishes that block into the blockchain. Jing started mining in 2010 using a very fast desktop computer to find a suitable proof of work for new blocks. As more miners started joining the Bitcoin network, the difficulty of the problem increased rapidly. Soon, Jing and other miners upgraded to more specialized hardware, with high-end dedicated graphical processing units, often used in gaming desktops or consoles. At the time of this writing, the difficulty is so high that it is profitable only to mine with application-specific integrated circuits, ASIC, essentially hundreds of mining algorithms printed in hardware, running in parallel on a single silicon chip. Jing's company also participates in a mining pool, which, much like a lottery pool, allows several participants to share their efforts and rewards. Jing's company now runs a warehouse containing thousands of ASIC miners to mine for Bitcoin 24 hours a day. The company pays its electricity costs by selling the Bitcoin it is able to generate from mining, creating some income from the profits. Mining transactions in blocks. New transactions are constantly flowing into the network from user wallets and other applications. As these are seen by the Bitcoin network nodes, they get added to a temporary pool of unverified transactions maintained by each node. As miners construct a new block, they add unverified transactions from this pool to the new block and then attempt to prove the validity of that new block with the mining algorithm proof of work. Transactions are added to the new block, prioritized by the highest fee transactions first and a few other criteria. Each miner starts the process of mining a new block of transactions as soon as they receive the previous block from the network, knowing they have lost that previous round of competition. They immediately create a new block, fill it with transactions and the fingerprint of the previous block, and start calculating the proof of work for the new block. Each miner includes a special transaction in their block, one that pays their own Bitcoin address the block reward, plus the sum of transaction fees from all the transactions included in the block. If they find a solution that makes that block valid, they win this reward because their successful block is added to the global blockchain and the reward transaction they include becomes spendable. Jing, who participates in the mining pool, has set up his software to create new blocks that assign the reward to a pool address. From there, a share of the reward is distributed to Jing and other miners in proportion to the amount of work they contributed in the last round. Alice's transaction was picked up by the network and included in the pool of unverified transactions. Once validated by the mining software, it was included in a new block called a candidate block, generated by Jing's mining pool. All the miners participating in that mining pool immediately start computing proof of work for the candidate block. Approximately 5 minutes after the transaction was first transmitted by Alice's wallet, one of Jing's ASIC miners found a solution for the candidate block and announced it to the network. Once other miners validated the winning block, they started the race to generate the next block. Jing's winning block became part of the blockchain as block 277316, containing 419 transactions, including Alice's transaction. The block containing Alice's transaction is counted as one confirmation of that transaction. Approximately 20 minutes later, a new block, 277317, is mined by another miner. Because this new block is built on top of block 277316 that contained Alice's transaction, it added even more computation to the blockchain, thereby strengthening the trust in those transactions. Each block mined on top of the one containing the transaction counts as an additional confirmation for Alice's transaction. As the blocks pile on top of each other, it becomes exponentially harder to reverse the transaction, thereby making it more and more trusted by the network. In the diagram below, we can see block 277316, which contains Alice's transaction. Below it are 277316 blocks, linked to each other in a chain of blocks, all the way back to block 0, known as the Genesis block. Over time, as the height in blocks increases, so does the computation difficulty for each block and the chain as a whole. The blocks mined after the one that contains Alice's transaction act as further assurance as they pile on more computation in a longer and longer chain. By convention, any block with more than 6 confirmations is considered irrevocable, because it would require an immense amount of computation to invalidate and recalculate 6 blocks. Spending the transaction. Now that Alice's transaction has been embedded in the blockchain as part of a block, it is part of the distributed ledger of Bitcoin and visible to all Bitcoin applications. Each Bitcoin client can independently verify the transaction as valid and spendable. Full node clients can track the source of the funds from the moment the Bitcoin were first generated in a block, incrementally from transaction to transaction, until they reach Bob's address. Lightweight clients can do what is called a simplified payment verification, by confirming that the transaction is in the blockchain and has several blocks mined after it, thus providing assurance that the miners accepted it as valid. Bob can now spend the output from this and other transactions. For example, Bob can pay a contractor or supplier for transferring value from Alice's coffee cup payments to these new owners. Most likely, Bob's Bitcoin software will aggregate many small payments into a larger payment, perhaps concentrating all the day's Bitcoin revenue into a single transaction. This would aggregate the various payments into a single output. As Bob spends the payments received from Alice and other customers, he extends the chain of transactions. Let's assume that Bob pays his web designer Gopesh in Bangalore for a new web page. Now the chain of transaction will look like Alice's transaction as part of a transaction chain from Joe to Gopash, where the output of one transaction is spent as the input of the next transaction. In this chapter, we saw how transactions build a chain that moves value from owner to owner. We also tracked Alice's transaction, from the moment it was created in her wallet, through the Bitcoin network, and to the miners who recorded it on the blockchain. In the rest of this book, we will examine the specific technologies behind wallets, addresses, signatures, transactions, the network, and finally, mining.